invert matrices. We don't want to solve linear systems. So we want explicit formulas that depend only on the average values at Tn. So whatever we're going to do, we're going to try to come up with a formula here that allows it, that only relies on data at time Tn, okay? So we still have to figure out what to do here. Well, the classic idea is to solve what's called a Riemann problem, okay? So a Riemann problem, otherwise known as sometimes a shock tube problem or a dam break problem, is to actually solve our conservation law at this interface, okay? But it's going to be a very special conservation law. It's going to be one whose initial condition is piecewise constant. And so we'll have a value on the left, a value on the right, and now we just allow our conservation law to evolve over a very short time step. Now you might say, well, wait a second. The whole point of this is that we don't know the solution to that problem. How are we now suddenly expected to provide a solution to what is actually a simplified problem, okay? Well, it turns out for a lot of very important cases, okay, all the ones that I mentioned earlier, we actually do know an exact solution to this very simplified problem, okay? And coming up with that solution is what's called, solving a Riemann problem, in case you've heard that term before. So, so that's what we're going to do. Okay, now I'm not actually going to go into the details, all right? There's lots of theory behind how to do this, and I'd be more than happy to provide any references if you're interested. But let's assume that we can and so what do we get? Well, so we start at time 0 with a situation like this. We allow our conservation law to evolve for a short period of time so that at some later time, maybe our solution looks something like this, okay? This is a bit idealized, but in, for example, gas dynamics or shallow water wave equations, we might end up with a rarefaction wave, a contact discontinuity, and a shock, okay? So, but the thing that's key is that over a short period of time, the solution here remains constant, okay? So we call this value Q star. And so really, when we solve a Riemann problem, we're interested in knowing what's the value of Q star at exactly this xi minus a half. Okay, and then the theory says that this will remain constant for a short period of time. Okay, so then there we go. That's exactly what we're going to do. We're going to define our flux as f. We have this function. This is given to us in our conservation law, evaluated at Q star. And we're going to say, well, that's an approximation to this thing that we needed. Okay. Now, this is what's called a classic Godunov scheme. It was developed by Sergei Godunov in the 60s, I believe. And it was sort of notable for resolving shocks in the case of nonlinear problems and rarefactions. It's conservative because every time we update a cell value with known fluxes at each edge. So unless we've got incoming fluxes at the boundary of our domain, the amount of stuff that we start with, we're going to have exactly the same amount of mass at the end. Okay, so that's the whole idea behind a conservative scheme, which turns out to be a really important property in lots of problems in, for example, geophysics, where we may not know a whole lot about the answer, but I do know one thing is that if I'm going to numerically evolve, for example, smoke or ash or something like that, then I want to know that my numerical scheme isn't somehow mysteriously losing ash or losing smoke, because that would be, a sure sign that there's something is maybe not right. Turns out it's stable, meaning it's stable up to CFL 1. It is an explicit scheme, so we are required we do have a time step restriction, but it turns out it's not very severe. But of course, it's only first order accurate. And you might see why, because effectively, since we're only relying on data at time level n, we're effectively, you could think of this as sort of a one-sided quadrature rule is kind of a simplified version of that, and we know that might only be first order, okay? So it turns out it's actually a very diffusive scheme. We don't like to use exactly this scheme in practice, But what people then have done, and loads of people have spent lots of time developing, schemes that will give us a better, more accurate interpretation of this approximation to this flux. The one that I've worked most closely with is the wave propagation algorithm developed by Randy Levesque. I've also been working more recently with somebody, Christiane Helzel in Germany, on a so-called active flux method that Phil Rowe has been working on for the last several years. And I mentioned Phil in particular because he, unfortunately, last week, he passed away. But he's been sort of a big name in developing a lot of these hyperbolic schemes. Bell Colella-Glaz was another big scheme that I believe Basilisk uses. There are muscle schemes, central schemes. There's all kinds of schemes for essentially evolving these hyperbolic conservation laws. Okay, nonlinear problems. Well, a common approach is to linearize using a row solver. Okay, Rowe was the first one that came up with, a way to linearize these schemes. And again, that's actually used. This approach is used by the codes that I work with. The wave propagation algorithm makes heavy use of a row solver. And of course, then the big challenge, I guess, becomes extending this to multiple dimensions. I described a 1D Riemann problem, okay? And you might think, oh, geez, if I have to go to 2D, how am I ever going to solve that thing in 2D? A 2D shock tube problem. Well, it turns out for a lot of schemes, you don't have to. You're able to solve 1D Riemann problems in one direction, 1D Riemann problems in a second direction, and depending, if you do things right, you actually can get a fully stable, accurate scheme that way. And then, of course, there are what are called unsplit schemes, where you do try to do work in multiple dimensions at a time. And those actually are the ones that I tend to prefer, are these so-called unsplit schemes. There are also people that will try to solve multidimensional Riemann problems, which can get pretty complicated. So I'm not quite sure how much progress has been made on that. Yeah, so that's what I wanted to say about finite volume schemes. And so now I'm going to move into adaptive mesh refinement. Okay. So the idea here now, we tend to work in a world that is, we like Cartesian meshes. Okay. Why? Because, well, first of all, early shot capturing schemes were developed for Cartesian meshes. Okay. A lot of the early schemes were just naturally, they were designed on these nice, regular, uniform meshes. Okay. They would map well to memory layout in modern architectures. The IJK indexing avoids indirect addressing needed for unstructured meshes. There's kind of a natural XYZ coordinate system, which often leads to more accurate, robust solutions. And for many practical problems, explicit finite difference and finite volume schemes provide very accurate, robust solutions on Cartesian meshes. And often this is the first mesh, at least kind of I feel like this is maybe almost a cultural thing, but in math departments, for example, it's often the first mesh that students are introduced to. In the States, I know in other places, it's often the first mesh everybody sees are kind of finite element type meshes, okay? But in a lot of the scientific domains that I work in, people often see these first. But of course, what's the big problem? Well, there's this so-called curse of dimensionality, meaning you have your nice solver that works, say, in 1 second on this nice coarse 8x8 mesh. And this is, of course, only in 2D. You now double the mesh size because, one way to get good accuracy for a finite volume or finite difference scheme is to reduce the size of your mesh. Okay, it's called H refinement for, I guess, the finite element world. But the minute you do that, you obviously now have 4 times as many grid cells. And if you're working with an explicit scheme, you now have to cut your time step in half. So you've now gone from a scheme that requires 1 second to a scheme that requires 8 seconds. And all you did was change one line in a configuration file that says I want to solve on a 16x16 mesh, not an 8x8 mesh. And suddenly you're wondering why your code that took 1 second or 1 hour suddenly now takes 8 seconds or 8 hours. Now, 8 seconds you might not notice. 8 hours you would notice, right? And now let's do it again. and we're up to 64 times, okay? And suddenly this gets really prohibitive. You've gone from 1 hour to 64 hours, which is who knows how many days, right? So that's the main problem with this. So, and here's just kind of a timing result. I actually went through and said, all right, well, let's just see how, is it really like, I can't believe it's really that bad. So I did a simple scalar advection problem, okay? And you can barely see that anything here is happening, but I take 40 time steps of a scalar, of an advection scheme on 128 mesh, 256, 512, 1024, 248, using this wave propagation algorithm. Okay, it's in a claw pack is the code that we often use. And I did this in my code, ForestClaw. Take 40 steps, 80 steps, 160, 320, 640. And you can't see this too well, unfortunately. But let's say that the 128 grid is our 1x thing. We increase, we double the spatial resolution and the temporal resolution. Now we're up to 6 times. Now what I'm doing is relative to each step. This is 6 times 1, 8. I double again. I'm increasing mine by a factor of 8. Double again, increasing by a factor of 9.9. Double again, I've increased by a factor of 11. So whereas each of these numbers should be 8, what we actually see is that they're actually worse than 8. Okay, and so we've gone from a problem which took a millisecond or less than 0.1 seconds to something now that takes several minutes, okay? And again, we don't worry too much about several minutes, but if you multiply this by, say, a factor of an hour, you're suddenly looking at, needing a significant amount of resources to solve this problem, okay? So we see a 5,000-fold increase. And so that's what's bad, all right? And the fact that it gets worse, it's worse than 8, probably has to do with poor caching memory performance on really large, when you're working on really large chunks of memory. So, well, you look at this problem and you say, yeah, there's not much going on here. I mean, blue is 1, yellow is 0. Why am I worrying about, the solver doesn't know that though. The solver just looks at 0 as any other number. It puts as much effort into solving a problem where the solution is 0 as it does to solving a problem where the solution is, say, 1 or some other non-zero value. So what's the answer? Well, one answer is to, if you really want to use these sort of finite volume, finite difference schemes, is to do what's called adaptive mesh refinement, okay? And so this is a technique that allows us to adaptively place computational resources only where they're needed. And here it's obvious that what we're trying to do is resolve this interface between 0 and 1. And I'll say more about what's going on behind the scenes here in this code in a minute. But let's just see how that does. And you might think, oh my God, but now you've got all this overhead. You've got to manage all these grids and who knows how complicated this is, and remeshing and doing all that stuff. That cannot possibly be faster. Well, it turns out it is. Whereas before, this number here was 222, it's now down to 17. So instead of a 5,000-fold increase, we've now got about a factor of 400 increase between our grid at 128 and our grid at 2048 by 2048. And now we go from, instead of increasing by a factor of 8 each time, we're increasing roughly by a factor of about 3.5 each time. So this is in 2D, okay? So 3D, I would imagine, and I haven't actually done the calculations in 3D, but at least in 2D. And you might say, yeah, but that's just a really simple scalar advection problem, maybe it would be well, in fact, since that is such an easy problem, it's a really lightweight solver, right? There's basically nothing that goes on. The Riemann problem is trivial. And so we're not hiding anything. We're not hiding anything in an expensive solver. And so any sort of inefficiencies in the AMR machinery is exposed. Okay, so we really are getting still really effective speed up. So here's just kind of a summary. On a single grid, big 2048 by 2048 grid might have taken us 200 seconds. Okay, and now if we say we skip, we're not really quite sure we want to do adaptive, but what we do is we divide up our grid into smaller pieces and somehow just solve individual blocks, but all uniform size on one processor. Well, already we can cut our time step in half by just doing that. And that has to do with the way that the memory is most likely has to do with, okay, no idea what happened there. Did it? It just decided to quit. Okay. Had, you know, so and already you can cut your time in half. Okay, so we increased by a factor of 1.9. Now, of course, now that we've got everything divided up into sort of smaller units, we can now suddenly talk about putting things on multiple processors. And of course, most laptops these days all have at least 8 cores, 16 cores. Who knows what they're coming up with next? If I put it on 4 cores, suddenly I cut the time again by a factor of 4. So this, you know, this is on uniform, no adaptivity at all. So now we've gone from 200 down to 30. Well, okay, as long as we're going to chop everything up, why don't we do it adaptively? Again, we can increase by a factor of 2. And finally, if we put that on 4 processors, we're now down to 5 seconds. Okay, which took originally 220 seconds is now 5 seconds. And that's an overall increase of about a factor 40. So this is why we do this, okay? Because we really can take there's huge software advantages. And if you're clever in how you do things, you really shouldn't see a lot of difference in solutions, okay? Now, of course, there's lots of questions you might have, like, really, can you really do this? And you know, who knows where we refine? I guess one more thing that we often do is what's called adaptive time stepping. So because we can take larger time steps in coarser regions of the grid, we tend to want to take larger time steps in the coarse areas and smaller time steps in the finer areas. And that can sometimes buy you a little extra efficiency. All right, so that's kind of why we do that. Now you say, okay, this is a great idea. I want to do this. How do I make my code adaptive? Well, you might Google adaptive mesh refinement and you find 1,000 places where codes that are doing adaptive mesh refinement in some flavor or another, okay? There's a whole Wikipedia page on adaptive mesh refinement. NVIDIA is somehow in the game. ECP was a big project sponsored, a multi-year project sponsored by the Department of Energy in the States that was making heavy use of adaptive mesh refinement. Lots of commercial codes have AMR capabilities, COMSOL, SolidWorks. I'm not sure what an ANSYS code, Basilisk, of course, maybe many of you are familiar with Basilisk. So, okay, well, and so just to sort of step back a little bit, you know, adaptive mesh refinement, the mesh is adapted to provide more resolution and spatially localized features of interest. So that's a key idea, is that it's dynamic. Okay, which a lot of times, especially I think I see this often in unstructured meshes, you know, they might do something like this, where they say, well, I've got some geometry here. I'm going to put refinement here, but the mesh is going to remain static. Okay, and that's fine. I mean, that may be exactly what they need. But in a case where you might have something like this, where you're actually, maybe you have a flow past something like this. If you're doing a dynamic calculation, you want the mesh to be able to dynamically refine. So these ideas are widely used in the CFD community, at least, and also in graphics. And this was an interesting figure I found on the Basilisk web page. I'm not quite sure I think this was demonstrating the volume of fluid methods. I'm not sure if something was solved on there, but it looked cool. So, so might be you know, I guess, yeah. So anyway, there's refinement maybe based on curvature or something. Okay, so I guess, what I'm going to talk about as far as AMR goes is adaptive mesh refinement is designed specifically to take advantage of Cartesian meshes. So you've got a Cartesian grid solver that you would like to somehow make adaptive or add adaptivity, which really isn't a thing that we can easily do. There's no compiler switch, at least not yet. All right. So if we're interested in time-dependent problems in which the mesh evolves dynamically. The goal is to make uniform calculations on Cartesian grids more efficient, but we also want to leverage legacy codes and solvers, typically finite difference, finite volume solvers. And the meshes should be locally as regular as possible, okay? So we really want to be able to leverage any existing legacy codes that are based on Cartesian meshes. And there's sort of three flavors of adaptive mesh refinement. And I've demonstrated one already, which is a kind of a hybrid approach, but I'll just briefly tell you about a few of the original ideas. So the original patch-based AMR was sort of this idea where you said, all right, I'm going to take a coarse grid and I'm going to layer on top of it finer grids. And I'm going to solve in kind of a hierarchical fashion. Solve first on here, then on here, then on here. Okay, now here you might say, wait, what happened to the grids? Well, one of the issues that comes up when you're demonstrating these things graphically, if I showed you the grid lines here, it would just be solid black. You wouldn't see anything. So we tend to hide the grid lines at the finer levels. Here you see kind of 4 levels. You see a coarse level. Might call this level 1, level 2, level 3, and then level 4. You see, in this original idea, which was developed by Marcia Berger in her thesis, the rectangles were allowed to be irregular, okay, not completely irregular, but were essentially unrestricted in the size. So you see some very tiny rectangles and some, very long, some sort of square, regular squares, and then some really long, thin rectangles, so this allowed for very efficient refinement patterns. And this is widely used in several big codes, especially this AMRX code, which was the basis for this ECP project, the exascale computing project. It's also widely used in 2 codes called AMRClaw and GeoClaw. Now, if anybody is working kind of in tsunami modeling, GeoClaw has become pretty widely used in tsunami modeling, debris flow, stuff like that. So this idea was kind of the original idea, still widely used. At the other end of the spectrum is, and I guess I called it patch-based. That's kind of my terminology. Nobody really has, because I thought it looked more like patchwork, something like that. Anyway, and some of the advantages is that it allows several patches of arbitrary size. Okay, so we can pretty efficiently refine. We can have flexible refinement factors. So between here and here, for example, I think there's a refinement factor of 4. It's a little hard to see, but this is 4 times the grid resolution of this. And that's actually pretty unique to this approach. I've seen people, especially in these large tsunami simulations, they have grid refinement factors on the order of 64 or 96. So it really means that you can really quickly, really efficiently go from really coarse to really fine really fast, okay? We use ghost cells around each patch. So halo cells, ghost cells, there's different names, which means that again, for hyperbolic problems that are explicit hyperbolic solvers, we can update individually on each patch. So that means that if you have a hyperbolic solver, we just have to plug it into a code like this, and we can make it work. So we can easily incorporate legacy codes, refine patches, you only refine right where you sort of tag based on refinement criteria, which I'll say something in a minute. And the downside is that there's lots of irregularity here, requires lots of complex data structures. So these irregular neighbor connections make some of the numerics more challenging. You're trying to apply a stencil in one of these little small areas, and you have to worry, am I too close to the next grid? What's going to happen? We have to update at all levels. That's not a huge thing. But initially, load balancing was a problem in parallel. So if you're working in parallel, you've got all these irregular size grids. You don't know quite how to distribute them to evenly in a parallel system. So then the idea was sort of go completely the other extreme, and let's make everything extremely regular. Let's have a quad tree mesh, and let's put a single degree of freedom in each cell. Okay, and several codes are based on this idea. DL2 is a finite element code developed in the Florida Colorado State University by Wolfgang Bungart, and he's done lots of pretty interesting geophysical problems. And this particular one is mantle flow. Ramses is an astrophysics code by Roman Tessier. Basilisk is an example of a single degree of finite volume code where each leaf is a single degree of freedom, a single cell average value. Okay, and this system has lots of appealing advantages. Refinement can be based on individual cells, so it can be really efficient and flexible. We can leverage technology for solvers from unstructured mesh community. And if you're using a flux-based scheme, hanging nodes, which of course we have lots of hanging nodes here, are not going to be a problem. One of the disadvantages, though, of course, is that you might have hanging nodes, and you might have the stencils are irregular in a sense that my neighbor to the right might have two cells here and one cell here, and I just have to figure out how to apply my update. Now, Basilisk has a really nice fix to this, so that essentially this problem is gone from the user point of view. Okay, and then refinement factors are limited to 2. Okay, so I don't really know of any codes that use the quad tree idea that actually allow for refinement factors greater than 2. And this can, sometimes people will say this can lead to over refinement because we're not able to really aggressively refine. I haven't seen it be an issue. Then there's kind of this idea that let's combine the best of both worlds. Let's do a patch-based scheme where we allow for grids inside of each little block, but let's use a quad tree mesh, and let's get the advantage of both. Okay, so that was kind of my idea, was to take, and that's what ForestClaw is based on, is this idea that we're going to have a quad tree mesh or an octree mesh, and it's a composite mesh in the sense that there are no longer any layers. Okay, and inside of each leaf, we're going to put a grid. And then that way we get to use our legacy Cartesian grid solver, and so we can, we don't have, say, irregular stencils. So again, there's several advantages. We can use fast tree-based mesh generators. We can easily incorporate legacy code. Using ghost cells, that is cells around the border of each patch, means that we can apply stencils fairly easily. We don't have, or at least it's not obvious to the user that there are irregular stencils involved. Load balancing is now trivial because we use what's called a space filling curve. We can enumerate all of these grids in one long line. If I have 4 processors, I take that long list of grids, I divide it into 4. You go this way, this way, this way, and this way. And again, using these space filling curves, and then because each grid requires the same amount of work, essentially. And so that makes load balancing trivial. And again, the algorithm that I've implemented uses essentially the original patch-based AMR algorithm. Again, but the disadvantage is that refinement factors are limited to 2, and refinement might be less precise because if I need to, for example, decide that this should be refined based on a single cell, I have to refine the entire grid. So that could lead to over-refinement. I haven't seen it be a problem, but that is sort of one potential disadvantage. So again, these 3 flavors of AMR. And the one that I'll say a few things now about ForestClaw is right there in the middle. So what is ForestClaw? Well, it's a parallel adaptive library that I've developed along with Karsten Borsted, and he's the developer of pforest, which is this high-performance mesh library. We like to think of it as being sort of, agnostic to what solvers you use. So if you're assuming you're working on sort of a Cartesian grid layout, you could use any solver you wanted. And I'll say a bit more about what's easy to do and what's hard to do. It's kind of a PDE layer. So we provide all the time stepping, the discretization, the interpolation, averaging that has to happen between grids, ghost filling. All that stuff can be user customized, but we provide mostly lots of defaults. We really like, mixed programming, C and Fortran, so we realize that a lot of the people that we work with come from backgrounds, they've got legacy Fortran codes, and they're, sort of okay with C, really don't want to deal with C++, so we keep it fairly straightforward in that sense. You have to know what a pointer is, but beyond that, you don't need to know much in the C world. We've got lots of extensions. So for example, GeoClaw is one of the extensions that we have. And we also have we've implemented basically the wave propagation algorithm as our solver. And we've gotten, one of the nice things, I've gotten lots of support from NSF, NASA, and DARPA to develop this code. And I'll say a bit more about the applications here in a minute. I guess one thing is, here's where I mentioned this ghost cells. So ghost cells are really this layer of cells around the grid. So this is a contiguous block of memory. And because we're going to use these ghost cells to kind of facilitate communication between grids. And here's just a couple of examples. Again, this is a problem that where I ran both Basilisk and ForestClaw. And it's not meant to show that, you know, I mean, this is obviously much more resolved than the Basilisk calculation, but just to give you a sense for how the refinement might look in both cases. And again, here I'm using each one of these squares is an 8x8 grid, whereas here each square is a single degree of freedom. I particularly like this problem because it makes such cool patterns. It's a shallow water wave equation in a box. It's pretty straightforward. Here's gas dynamics. So this just shows you sort of how the dynamic meshing kind of works. This is a shock hitting a low density bubble. And that bubble, you can really see the refinement is really picking up a lot of these really small details of the density, the low density bubble. So how does the initial mesh creation work? Well, the idea is you basically start with a sort of a min-level mesh. You initialize your problem, and then you successively iterate until you've refined to the sort of a level that you're happy with, okay? So each time you decide that, okay, here I needed to refine, you know, I want to refine every place where the interface, where a grid might have values that contain both 0 and 1. So somehow I want to refine around that interface, that 0-1 interface, and we do that until we have a nice initial mesh that we're happy with. Now, in the process of doing this, lots goes on behind the scenes. We had to destroy these 4 meshes here and replace them with 16 meshes, okay? So somehow there's a lot of memory allocation between here and here. And the initial mesh we didn't need to interpolate because we can always go back to our initialization routine to redefine on that cell, okay? Now, once we've got things going, we want to dynamically be able to go from this configuration to this configuration. So again, what happens? Well, we decide that these needs to be coarsened, for example, because our blob is moving away. So we coarsen here, and that replace these 4 grids with 1 coarse grid. And here we decide that the blob is moving in this direction. And so this grid here needs to be replaced by 4 finer grids. And that happens using processes, and again, averaging and interpolation. And because our schemes are typically second order, we can do second order interpolation. Averaging in a finite volume scheme is exact, right? Because we're tracking the cell average in each cell. So the cell average on 4 cells can be simply, we can do an arithmetic averaging to get the average on a coarser cell. I've mentioned ghost cells several times. Well, this is how we communicate between grids. We need to either copy data. So all of this, keep in mind, has to happen in parallel, okay? So a lot of these patches will be existing on different processors. So all this has to happen, you know, in a fairly complex, this is probably the most complex part of the algorithm, is getting all of this to work in parallel. Okay, so we might copy data from one grid to the other, or we might average fine grid values onto coarse grid ghost cells. And here we might interpolate. So for example, I need corner values for this grid. I need to interpolate from coarse grid values. Or here I need fine grid values here. I'm going to interpolate from my coarse grid to the fine grid, okay? And this requires careful coordination because when you do this interpolation step, you better be sure that the coarse grid has valid coarse grid values that maybe were copied from a neighboring cell or something like that, or interpolated in this case. So there's a fair amount of choreography that has to happen to make sure that this interpolation step will always be working with valid data. All right, so this is kind of a long thing, and I want to show you some applications here. So there's we use mainly what's called feature-based refinement, okay? That is, we look for sharp gradients, we look for sharp jumps, and this was all kind of based on the original shot capturing ideas, okay? So we really don't do anything terribly sophisticated. There's lots of other ideas. So Basilisk uses a really clever kind of wavelet-based refinement. There was initial ideas to use Richardson extrapolation, although we've sort of jettisoned that because it got too complicated. Adjoint methods are sometimes used, and I've recently come across some work. There's a student in our department that's working on deep reinforcement learning for adaptive mesh refinement. I'm not completely convinced it's a good idea, but I haven't looked enough into this. Why don't we do something fancier? Well, it's hard, okay? A lot of these complex multi-physics problems, we don't know how to do error analysis, basically. But there's lots of work that can be done. And I guess we sometimes will also say, well, look, you know, the truncation error is often, for these finite difference, finite volume methods, we know that the truncation error is proportional to gradients, curvature, large jumps in the solution, etc. So those features are actually not completely unreasonable to refine around. And then for many applications, we kind of know that if we're doing tracer transport, for example, there's no error where there's no tracer. So the error is 0 there. So we're not even going to bother. There's no point in doing error analysis. We're just going to make sure we don't devote a lot of resources to areas where the solution is 0. Nonlinear problems, of course, are always a challenge. And then what we will often try to do is make sure that the finest grids keep the solution that we care about, the wave that we're trying to track, or the ash cloud on the finest levels so that it's not allowed to escape. And that might be viewed as kind of cheating, but for large domains where there's only a small cloud of ash, it's actually not a completely terrible thing to do, or at least to fall back on. Okay. ForestClaw, what's easy and what's hard. I think I'm going to skip this step. Explicit things are easy, implicit solvers are hard. And now I want to show you some applications. So I've been involved in several applications. Smoke transport problem where we're actually doing some data assimilation. Okay, that's actually turned out to be really challenging, but also a really a fun project that we're just now sort of getting some interesting results from. We're modeling, we've got a project involving this atmospheric lamb wave that was resulted from the Hunga-Tonga eruption back in 2020, I think. I can't remember, 2012, 2022, can't remember. It's recently. GeoFlood, which is an overland flooding code based on ForestClaw. A direct solver, this was a student who developed a direct elliptic solver for the ForestClaw meshes, which is a particularly challenging thing to do. An early project I did was take a legacy code developed at the United States Geophysical Survey and port it to ForestClaw. And then I'll say something in particular about a thunder egg, which is an elliptic solver that we've developed, third order active flux, and then a code that, and I'll say an application that I've been recently most involved in. So this is an example of one of the types of problems I've been involved in recently. The idea here is that we, and this is a code I wasn't developed, they basically took ForestClaw and developed their entire code in ForestClaw. So I'm not the expert in this application, but the idea is that we have an atmosphere and we have some kind of disturbance. Here you can see the results of the disturbance. And we want to understand how that disturbance propagates into the upper atmosphere, because we can actually use GNS, so receivers, satellites, things like that, to detect the signal in the upper atmosphere and use it as a possible way of detecting these terrestrial disturbances. So for example, and this was all funded by a project called AtmoSense, using the atmosphere as a remote sensor. Here's just another example. This was the one of the things that this project, it was a 5-year project funded by DARPA, that which is the defense agency in the U.S. Allowed us to do was develop a full 3D version of ForestClaw, which we didn't have up until about 5 years ago. This is a related project, is code in the ionosphere. So this has to do with development of things like auroras, you know, northern lights. And this code, again, you know, they took their version of the code called Gemini, ported it to ForestClaw, and are now doing their aurora simulations using ForestClaw adaptivity. And they've seen some tremendous speed at both of these codes. I mean, I hear factors of 200, for example. They just simply wouldn't be able to do this without ForestClaw or some kind of adaptivity. What we've done recently is coupled these two codes, this magic code and the Gemini code, into something called figments. And so this, and the interesting thing here is that these Gemini project uses a mesh that looks something like this sort of arch thing. It follows along magnetic lines. The magic code is either this square box or this, in this case, a cylindrically symmetric solution. The meshes don't know anything about each other except that they're two ForestClaw applications. And we can now, in runtime, couple these two solvers in a way to produce full solutions that go from the ground, the terrestrial, up into, I think it's up to 200, 400 kilometers and above. And so these are just some of the results of this propagating wave into the ionosphere. A project that we've now just recently got another 5 years of funding to continue this project. And one of the things that we're now working on is developing a potential solver. So we actually already have a solver called Thunder Egg that is an iterative solver for these adaptive meshes. And so this is a kind of a test problem. And one thing that, so this is a 2D cross section through that sort of arch. Okay, and this was kind of an initial test problem. And you can see right away, one of the challenges is going to be that we have to deal with these far field boundary conditions, and because this is not a reasonable solution to a Poisson problem in the far field. And then finally, I've been working on some higher order solvers. So this is this active flux method that I mentioned earlier that we've developed an AMR version of this solver. And this is really an example of something when I started AMR-Claw or ForestClaw, I really said, you know, I want something that people who develop numerical algorithms can actually use to think about how to solve things with AMR. Because one of the big disadvantages of adaptive meshing is that the codes are so complex that nobody is thinking about how to do any kind of sophisticated time stepping, you know, how to do more than second order. You rarely will find, I think Stefan has worked on some higher order methods, but they're typically not, it's not very well researched area. And this is an example where, and it was a colleague of mine said, oh, I think we can take her algorithm, this active flux method, which was initially developed by Phil Rowe and several others, and let's see if it works with AMR. And it turned out to work really well. So it's a scheme in which we track not only the cell average, but also point values on the boundary of a cell. And we use those to use sort of a Simpson's rule to actually come up with accurate approximations to that flux integral I showed you at the beginning. And so this leads to a nice third order scheme, which is particularly good when we're trying to track, say, acoustics waves over long distances. And that's it. And I could be happy to say more.
Thank you very much, Donna, for a very nice talk. Are there any questions? Yes?
Thank you for this really nice talk. I appreciate it a lot that you started from numerical schemes and finite volume methods and progressively you went to IMR. So my first question is specifically related to what you said, I think, at the end of the presentation, but just to be sure, if you do have this idea or this philosophy of doing IMR, I'm particularly convinced that you cannot do IMR without looking at numerical schemes. You
Exactly.
have done lots of work on numerical schemes. So do you agree that you cannot just adapt the mesh because you have a tool? You also need to look at the schemes that you're having to solve on these kind of meshes.
Yeah.
And this is related also to the limitations of octree that you can only refine by a factor of 2. Do you think you can increase this factor by working in more efficient numerical schemes, or do you think these limitations of factor 2 is not related at all to the numerical scheme? So it's like 2 questions in one.
You'll find 8 questions in one. Well, okay, so it's absolutely true. So when AMR was first being developed I would say in the mid-90s, there was this, especially the group that developed this AMR Xcode, the original patch-based idea. They would say, oh, you have a solver, we're going to put it in AMR. And then, and so some advisor would hear of this idea, would send his graduate student or her graduate student, go work with AMRX people for a month, and let's get an adaptive code. And if you sat in their office and they had and you were able to fund them somehow, they would help you get your solver implemented in AMR, or they would just tell you, no, you have to use our solver, but if you want to do an application. I guess the point is that it was never as easy as they said it was. Okay, there was way too many. There's things that happen at these boundaries that I've completely brushed off. How do you maintain conservation, for example, when you have different levels of grids? How do you do elliptic solves consistently? So you definitely need to look at the solver. The quad tree issue. Initially, I thought we were going to actually try to do something where we could do factors of 4, factors of 8, because it seems like you could just kind of maybe skip levels in your quad tree and just jump from level, a 0 level to a level 2, for example, and skip an intermediate level. So that's kind of a software issue. And that's already probably somewhat challenging for codes to handle, because oftentimes this factor 2 is hardwired everywhere. But then the numerical question that you asked, is it a good idea? And I don't know. I mean, like I mentioned, there are codes that are using factors of 64. And I kind of think, well, I guess. I mean, they're doing these in large tsunami models where it's probably the case that, at the boundaries of these coarse fine patches, essentially nothing is happening. So yeah, okay, they get away with it. Whether I would, probably you need a pretty robust numerical scheme to handle that. Maybe a higher order scheme, because now you've got 4 fluxes that have to replace 1 single flux. I don't know. I haven't really even thought about that too much, but probably for some schemes it's okay. I would guess that there are other schemes where you're going to have to think really carefully about how to even do AMR from level 0 to level 2, for example. I don't know if I answered that very well, but it's a good question.
I have a second question.
Yeah, okay.
So you showed unsteady simulations.
Yeah.
How do you deal with the unsteadiness? Are you adapting at each time step, or do you have
Yes.
some algorithm that adapts whenever you feel that the error estimator is evolving or is showing some interesting features? How do you deal with that?
I do it at every time step. And often the advantage of doing it at every time step is that not too much is changing from one time step to the next. And so you're often then able to really keep the thing you care about on the finest level. If you wait too long, it might, leave the fine region, and you're now in a situation where you're not going to be able to recover because, the blob that you were tracking. And we're really thinking about situations where AMR is the appropriate thing to do. Okay, so there are cases where it's just doesn't make a lot of sense. But in the case where you have some really localized feature, you don't want it to leave your fine grid region too quickly, right? So I tend to do it every time step. In the original schemes, there was a parameter that you set, every 3 time steps or every 10 time steps. But I guess the point is it can be done really efficiently. And that's partly because I'm using this pretty efficient underlying pforest meshing algorithm, meshing software.
Thank you for the talk. And I saw that on your website that in 2018 you tried to do a ported to GPU.
Yeah.
the forest code, and have you been successful with it?
Yes.
And if so, how do you deal with the, like you said, every time that you update the mesh, and is it because you are doing patch based that it's more efficient that way, that you don't have all those tree traversals and the pointer
Yeah, let's see. I mean,
problems that
yes. So let's see here. Okay, so here's, I guess I have one picture here based, so here's the kind of the, how we do this on GPU. So a lot of stuff we leave on the CPU, okay? All the mesh management, the adaptivity, all that stuff's on the CPU. The only thing we port to the GPU is at every time step, we create a big stack. So because all of our grids are the same size, I mean, this is gonna sound horrific, like this can't possibly work, but we take all of those patches, which are all just living in memory wherever they are, copy them to one giant contiguous block of memory, send them all off to the GPU, and then in the case of 2D codes, I'll admit I haven't extended this to 3D yet. So this was an idea we developed I spent about 3 weeks on it several years ago, and haven't revisited it too much. But the idea is that we then use these all get sent to a third dimension of thread blocks. Each patch then is given a certain number of threads, and we just march, say in this case, 32 threads along our cell, okay? And so all of these are being worked on simultaneously on the GPU. And I guess it has, because we're doing an unsplit scheme, the patches are all the same size. This can be done pretty efficiently for explicit schemes. And here's some of and again, these timing results aren't great because all I did was compare a single CPU to a single GPU, which really isn't the right comparison. You should compare a node of 24 cores to a single GPU, because that's where if you're buying these things, you want to know, should I buy another CPU node of 24 cores or 48 cores, or should I buy a fancy GPU? But this just illustrates that what we were able to do was take this, basically, this is the piece that's on the GPU, and we are able to cut this blue thing down to essentially nothing, okay? And so this advanced step is basically the solver. So it basically goes from here to here, okay? So that was kind of the big savings. Everything else, this obviously, none of this changed. What's that big blue thing? Is the ghost filling. All the communication between ghosts, that's all done on the CPU. So obviously that doesn't change, but as we go to multiple processors, you notice that gets smaller and smaller. So now we're kind of in the noise here. I ran this on 16 processors, so 16 GPUs. Now again, whether this was a great, I mean, this particular code I talked about, GeoFlood, he runs on GPUs he just says it's just faster. So, and it doesn't affect the solve at all. So he just runs on GPUs whenever he has GPUs. So in that sense, it definitely pays off. But you'll notice that the things that don't show up very much are these copies. So that's this stuff right here. This is the copying between the CPU and the GPU. And obviously, it gets less and less as we go to multiple processors because we're doing less copying per processor. I just gave you my spiel. I'm not sure if I particularly answered your question.
This is with explicit simulations?
Yes, just explicit. Okay. So,
have you tried with implicit solvers at all, or like multi? No.
Do you want? You could. Do you want a project? We have a multi-grid solver. We have not yet tried it on the GPU.
Thank you.
So our P4S meshing, everything lives on the CPU.
Thanks.
Mm-hmm.
So at each time step, you're adapting your mesh.
Yes.
Could you adapt it once more at this time step? Would it change something? Adapting twice at the same step?
I think I know what you're getting at. Like if we adapt once and then I say, let's just do it again. Is there any kind of hysteresis effect or something that maybe goes back and forth, or we don't do that, but we do have to be careful. So for example, we have a refinement criteria which says refine if something exceeds a value. And we have a coarsening criteria which says coarsen if 4 grids, you know, don't satisfy your coarsening criteria. And we want to make sure that that coarsening criteria, the rule of thumb is should be half the refinement criteria, so that you don't go back and like re-refine something that you've just coarsened. And so that's how we try to avoid that. Yeah.
And if you were to do a static computation, just so you could do a first static solving and then
Just never
adapt
refine.
and more. Yeah, but you could do it once more. Once you refine, you solve again the equilibrium.
Oh, retake that time step. I see. I'm not sure.
We'll discuss this later.
Okay. I see. Maybe it's a way to do error analysis or something.
Maybe
Yeah,
we'll stop
okay.
now, but Donna is here until the end of the month, so don't hesitate to contact her or contact me if you want to talk with her, because Donna
I'm
will
around,
do that
yeah.
time, and she will be around, so don't hesitate to do that. And thank you
Yeah,
again, Donna.
good. Thanks.